Great. So the last class we were discussing relational algebra. Relational meaning relations. Here, relations are something like tables with some extras. Algebra meaning that there's operations that, given two different relations, this is an operation or a set of operations that you can do on different relations. Okay. Now there are 7 operations: the union, the intersection, the set difference. The union combines 2 relations together. You can kind of view this as taking one relation and then appending another relation sort of vertically, if you like, appending different rows. That's what the union does. The intersection is when 2 different relations have similar entries and you're keeping only those. The set difference is subtracting entries from one relation to another. The cross product is an important one that we'll come back to again and again. The cross product finds all possible pairings between 2 relations. So if you have one relation A and another relation B, every row of A is going to be paired with every row of B, or vice versa. The result's the same. So that's the cross product. Projection is relatively easy. All that projection does is sort of selects columns of the relation. The select operator selects rows as opposed to columns. That's the difference between a project and a select. And then there's the rename operation, and that's very simple. It just changes a column name from one thing into another. I left this as a practice question, the last class, a natural join. And if you reference the Database Management Systems book or other sources, you might see join operations. Now, the join operation takes 2 different relations and finds those rows where an entry exists for, let's call it A, and an entry exists for B, such that there's a common characteristic. So that is a natural join. I left it as an exercise to see if you guys could figure out, using the other operations, to construct the natural join. So let me pause and see if any of you have thoughts on that or ideas. The natural join. Nobody. Okay. Let me start there. And as a motivation for how to use these operations to do things that you care about. Let's take the example on the screen. We have one relation A that has an entry in the name column for John. There exists another relation B that also has a name column that also happens to have the name John. So the point of the natural join is to combine A and B, these two relations, where there's a common entry. Okay. Now, in this class, for this semester, I am going to not allow anybody to use joins straight. Like, you have to reconstruct a join using more primitive operations. What I mean by that is, so here's number 7 with the rename. We have 7 operations that you can use, and that's it. If you want to do a natural join, then you must use one of these other, a combination of these 7 operations. So again, the idea here is to have 2 different relations and to combine them together in one relation, or one table, if you like, where attributes from one and attributes from the other are combined together. So here we can see this relation A that has entries about names and ages. And then there's another entry B that also has names, but an address. And the goal is to combine these together such that similar entries are put together and combined in this way. Okay. Now, how can we use the above primitives in order to do this? So first of all, this name column, we're going to rename one of these. So this way we're not confused. Insofar as when we're referring to a name column, that it's clear if we're talking about this name column, that is the name column of A, or the name column of B. Each of them have a column called name, but we're going to rename one of them so that way we don't mix the two up. So, okay. So, first of all, we're going to make the name column of B, let's say, we're going to rename it from column name to, I don't know, name 2, whatever, of B. Okay, so what this does, this row, which is a rename, again, this row That's an R for rename, whatever. It's just renaming a column. What this does that I just wrote is it takes the relation B and that name, it replaces it with the name 2. Okay? So what I've written on the bottom of the screen has this effect at the top of the screen. It renames a column. Okay? So now we have two different... when I say name, that's going to be different than when I refer to name 2. So this way we can differentiate names from two different relations. Okay. So that's the first step. The second step is that we're going to take A and do a cross product with this renamed column of B. So this, the cross product, is going to, let me move this. This is what we're trying to reproduce. Okay, this is the end goal, right? This sort of bow tie operation. We're not going to be using it. We're going to be reproducing it with other operations. So this is the end goal. This is what we're trying to end up with. Okay. So when we rename a column of B and we make a cross product with A, let me pick on somebody. How about Jonathan? You have Mike?
How are you doing? How are you doing, Professor?
Okay, and apologies for being late. Thank you for sticking around. What will this produce when we take A and we cross-multiply it with this?
So you get a table with 4 columns and
Yeah.
4 entries. So you have John 18, John 1 Ave. You have John 18, Susan. I don't know what that address is.
Yeah, 2 Street.
Oh, 2 Street. Sorry about that.
That's fine.
And then you have Paul 19, John 1 Ave. Paul 19, Susan 2 Street.
Wonderful, thank you.
No problem.
And let's see, Paul 19, and then here we have Paul 19 again, and Susan 2 Street. Okay, now this is the name column, this is an age column, this is now name 2 and address. Okay, so a row B. I'll write the row without this, just to make things a little bit simpler. Excellent. So now this is, again, every possible pairing. So John gets paired with John 1 Ave, and John 18 also gets paired with Susan on 2nd Street. Similarly, Paul gets paired with John on 1 Ave, and Paul gets matched with Susan on 2nd Street. So there's 4 entries here. Excellent. So this is all possible pairings. Now this is going to create a relation with a lot of trash. That is, this new relation is going to have a lot of entries, many of them that we don't care about. The ones that we do care about, again, we're trying to find those entries with the same attribute. So here, John, there you go. Okay. this is really the only entry that we care about, because John appears twice, which means that John exists in both A and B. You'll notice here, John and Susan are different names. Paul and John are different names. Paul and Susan are different names. So the only one that we want to keep is the first entry. And so for that, we're going to do a select where name equals name2. Okay? This will have the effect now of taking all of this, which is here, and only keeping this, because here name, John, equals John, name2. And now, because there's one repeated entry, which is to say John and John, and we don't really need the repeat, we are going to project the name, age, and address of this. Okay? So a project deletes a column. So what this effect is, the project, is it gets rid of this, and it will now return just this single entry, right? John equals John, and this is exactly the thing on the left. So you can, it's simpler to write this symbol, right? A kind of bow tie where you're matching the name. That is much simpler. For this class, I am barring any student from using the word join in any context. I know it's simpler. The reason for me doing this is to make sure that students know what's actually happening. When you do a join, all of this, is actually what happens under the surface, if you like. Wait, how did I get rid of the last 2 rows? That's this. The select. I'm selecting only those rows where name equals name2. These. Okay? So, looking at this part, A cross this renamed B produces this table here. And now with this select, deletes rows, right? So now we are demanding that that entries in the column name must equal entries in the column name2. Here, John does not equal Susan, so that gets taken out. Paul does not equal John, so we take that out. Paul does not equal Susan, so we take that out. That's what the select does. With the project, this is very close, this one. The first row to this thing on the left, but there's a repeated name, right? So in order to get rid of the repeated name, we do a project to delete this thing. That's what the project does. And now we have John, 18, and who lives on 1 Avenue, which is exactly this on the left. So should we all start working inside and then moving our way out? Because if we did project first, we wouldn't be able to select since name2 is deleted in the project command. Yes, that is the way that this sort of works. If you like to think of it this way, you start kind of on the inside and then build out. That's the way to construct things. Okay. So to repeat, this join operation that looks like a bow tie takes two relations that have a common attribute. In this case, that's name. And the result of this is combining different information that each of these relations have together into one relation. You can write this simply using this bow tie notation. Okay, so that's what in this case, a natural join. There's different joins, a left join, right join, whatever. I'll leave that up to practice for you. But this is the result of a join operation, is combining two different relations such that the entries are a combination of the attributes of the rows that share a common attribute. In this case, name. It's very simple to write it this way with a bow tie. Okay? But for this class, I'm enforcing not doing this simple thing because in my experience, students sort of view this as some kind of magic, right? You just do a join and things work out or something like this, which is not what you should be doing. You should really understand what's happening. And if you actually look under the hood of what a join is doing, it is this. Okay? It's a rename, a cross product, a select, and a projection. It's all of those. This isn't just another way to do a join or a natural join. This is actually the way that a natural join is computed. And so this is what I want you to understand. And after this class, you can use join. Okay? There's nothing wrong with it. But for this class, I'm enforcing that you do the lower level operations. So this way, you actually understand what a join is doing. It's not magic. Nothing fancy. It's this process. Okay? After this class, go ahead and use a join, because I will feel confident that you'll understand how a join actually works. Okay. Another thing to appreciate about the join is this one right here. That's the cross product, which is finding all possible pairings. And that is an expensive operation. What I mean by expensive is if A has n rows, okay, n is 100, whatever, a bunch of rows, n of them. And then B also, let's say, for example, also has n rows, okay? Lots of rows, n of them. Then A cross B is going to have n squared rows. So here, if n equals 100, then that means that this is going to have 10,000 rows. Okay, so you have two tables. Here's one with 100 rows. Here's another with 100 rows. When you cross-multiply them, it has 10,000 rows. Most of them are trash, but this is the result of the operation. And that's what I mean by expensive. That you're multiplying the number of entries of one with the number of entries of the other. And this can blow up. 100 rows isn't so many. If you make it 1,000 rows each, then it's 1,000,000 rows that you end up with. So things blow up. This is what I mean by expensive. Okay? This. And the join does this behind the scenes. Okay? It's doing a cross product. You don't see it, but under the hood, so to speak, that's what's happening. And hopefully by the end of this class, you will have this absorbed, that cross products are expensive, and therefore joins are expensive. Which is to say, just don't use joins carefully. They're useful, but if you're joining things left and right, that's a big waste. You should try to avoid joins if you can. The reason for that is this. Exactly this. That there's a cross product involved and things can blow up. So sometimes you can use a join because you have no other choice. But you should not just be throwing around join this, join that, join, because it gives you the right answer. Because it can be really expensive to do this. And here is why. This is actually what a join does. And in this class, join, the word is banned. Instead, you have to use this sort of lower level thing. So you can reproduce a join with renaming, with a cross product, a select, and a project. So with those four operations, which are lower level, meaning you cannot reproduce them with other operations, join is a higher level operation because you can do the same thing with other simpler operations. And so that is why I'm saying that for anything relational algebra related, you'll notice here, 8. I labeled this number 8, the 8th operation, because that's what the book does. But you actually don't need this, right? This is an extra thing that saves you notation. But actually, you can delete this natural join operation, and you don't need a bow tie to do stuff. You don't need this A bow tie name B, because you can reproduce the exact same thing using other operations. Fine. So let me pause and see if there's any questions about any of this. Otherwise, I will move on. No questions. Okay. All right. Let me do this. Start a new page. We'll call this example 1. Okay. So for the next, for this class, next class, what we're going to be doing is going over different examples of how to phrase a query. So a query means that we have more than one relation, and we're interested in taking these relations, maybe combining them, and then keeping only those rows that match some criteria. Okay. Let's see. Let's make this name, age, gender. Now, this is the so-called schema. Sorry. Here. And I'll make that text bigger as well. Let me do that now. Okay, all of that. Wait, can I do the whole thing? Perfect. Okay. So this is called a schema. Okay? A schema is the number of columns, their names, and their types. So here, name, this is a string. Age is going to be an integer. And gender is also going to be a string. Okay, so that is a schema. It's column names and their types. This, in short, kind of describes what this table or this relation is about. No specifics, that is to say, what the actual entries are, is not a part of the schema. The schema is only describing kind of the type of table this is. So here, we do John, who's 16 and a male, and Peter, 18 and a male as well. So these entries are not a part of the schema, okay? A schema is just the names and types of the columns. The entries themselves are I don't know, more specific or something. Okay. Oh. And insert. Oh, that's what I want to do. Here. Okay. I'll call this the person table. The person table. Write this here. That is a schema. Now this is going to be a frequents table. And these we'll use as sort of running examples, if you like. Okay. So here is name, and that's going to be text. And restaurant, which is also going to be text. Or a string, sorry. Okay. Now let's say Mary frequents McDonald's. Susan, Susan frequents Henry's. And John frequents McDonald's. Is that spelled wrong? Is that how you spell Henry's? Maybe. Okay, fine. Okay, so this is, I'm going to define 4 different relations. Not all of them are going to be relevant to the query, but eats and serves. Okay. Well, okay. Name, string, food is also string, serves, string, some food with, this is like a menu, the serves. So string, and actually I want to add a column here. Okay, and a price. That's going to be a float. So here, John likes to eat burgers. Susan likes to eat fries. The restaurant, McDonald's, serves burgers for, let's say, $2. McDonald's serves fries for, let's say, $1. And fine, whatever. We can expand these things later. Okay, now we have 4 different relations, where a relation is a schema plus rows that fulfill that schema's description. So here we have 4 relations, one named person that tells us about the person, their age and gender. Frequents is a relation that describes people in the restaurants that they frequently go to. Eats is a table for people and the food that they eat, and serves is a table that is about restaurants, what they serve, and how much that costs. Okay. Now, let me... What time do we have left? 2:51. Okay. Find all restaurants frequented by at least one person under the age of 18. Now, this one I'll do for you. The next one I'll give, and I'll try to move faster. I'll let you do. But just so you know how things go. Now, here are 4 relations and 1 query. The query is this. That's in human language. Find all of the restaurants that are frequented by young people, like under the age of 18. Okay? Human language query. Let's write this query using the operations of relational algebra. Okay? So, this is really simple. Okay. Let's look at this query. We're interested in restaurants that are frequented by people, and we know their age. Okay? So people and their age, we can get from that relation. Frequented restaurants, we can get from that relation. The eats and serves relation are extra. They're not relevant to this query. Okay? So, how do we write this query? Okay. So for this query, we're only concerned with 2 relations. That is the person relation and the frequency relation. Each of these have a name, which is how we're going to be matching them together. So let's take, switch, there we go. Let's take the person column, and we're going to pair this, that is cross multiply, all possible pairings, with the frequency relation. Okay, because we want to find which entries do we know about people and which entries do we know about restaurants that people frequent. And here this has the age that we care about, and that has the name of the restaurant that we care about. Each of them have a name, and it's on the name that we will be matching things. So here I will do name, let's call it name 2, whatever, of frequency, okay? Now this is going to create a relation of 6 entries. I won't do it now for the sake of time, but that's going to be John matched with Mary, John matched with Susan, John matched with John. That's the one that we care about. Peter matched with Mary, Peter matched with Susan, Peter matched with John. Most of those are trash. So that's what this cross product is going to be doing. We'll have a table of 6 entries, 6 rows. Okay. Now, of these rows, we're going to select those where the age is under 18 and where name equals name 2. Make those capital N's. Okay? That is to say, of these 6 entries, 1, 2, 3, 4, 5, 6. John matches, that's where name equals name to. So we keep that entry. All of the others we delete. Okay, so of these 6 rows, we're only keeping one of them because only the name John appears in both. And finally, we can project the restaurant. Okay, because we only care about the name of the restaurant. We don't need any other information, age, gender, name. That's not the question. The question is about restaurants. Return to me the name of restaurants that do this. And so that is how we would realize this query. What the result of this query would be is a table restaurant with McDonald's. Okay, that's the result of this query. So McDonald's is the name of the restaurant that's frequented by at least one person, John, who is also under the age of 18. So this is the way that things go, okay? We will have different relations. In fact, it will be these 4 relations. With a query in plain human language. And the question is, how do you phrase this using the 7 operations that we talked about before? Okay, now, I was hoping to have more time. My fault for starting class completely. But just because I don't want to keep you over, but maybe you can get some practice. Let me give the setup for the next question. Let me copy these. Perfect. Oof. Okay. Oof. Oh. Boy. Let's see. Who cares? Yogurt. So, okay, great. And now here's the query. Find the names of all females who eat either yogurt or salad or both. Make that bigger. Okay. And this is what I will leave you with. Let's make that bigger, like that. Okay. So, given these 4 relations, you don't need all of them, and in fact, you only need 3, or 2, actually. Write the query with relational algebra that will return all of the females that eat either yogurt or salad. just to give you a quick sanity check, that will be returning the name Amy and the name Jane. That's what you return, because Amy and Jane are both female, and they both eat either yogurt or salad or both. I mean, some combination of them. So how would you write this query? That I will leave as an exercise, and we can pick it up on Wednesday. So thank you for staying a little bit over, and that's the end of today's lecture. I'll hang around for questions.